Hi, my name is Justin Xie. Welcome to my presentation. Today I'm going to present a paper review that I found on the IEEE Transaction and Parallel Distribution System. This paper is published in 1993, and the paper title is Strategies for Dynamic Load Balancing on Highly Parallel Computers. This paper is like 30 years old, and there are some reason for me to choose this paper. The first reason is because I'm new to this area, the parallel computing. Maybe an older paper is easier for me to understand some terminology or vocabulary related to the parallel computing. And the second reason is because the CPU is related to our project. My project is the neural network. Sometimes when I train the model on my computer, because my laptop without the GPU only has the CPU, sometimes when I'm doing the debug, I need to use my laptop CPU to run some model to debug the problem. And I try to get to know, maybe have a better idea to understand how is the CPU doing the parallel computing to accelerate the calculation process. Okay, let's look at the overview of this presentation. First, we're going to talk about the problem they see and give out the solution. Next, we'll talk about the implementation, and last, we'll talk about the result they got. In the first slide is about the problem. Multiprocessor system has been shown to really efficiency as shown in the uniform computation and uniform problem. But however, the large cost of non-uniform problem with uneven and unpredictable computation are not easy to solve. In this paper, they compared 5 different dynamic load balancing strategies. The first one is sender initial A diffusion, and the second one is receiver initial A diffusion. The next one is the hierarchical balancing method. The next one is a gradient model, and the last one is a dimension exchange method. For these 5 dynamic load balance strategy, they are focused on 2 different trade-offs. The first one is the knowledge. The knowledge means is the accuracy of the each balancing decision. And the next one is the overhead. This slide talk about the 4 phases for the general dynamic load balancing model. The first phase is the processor load evaluation. It estimates the load value for each processor. And the second phase is the load balancing profitability. This phase determine the load balancing is profitable or not. And the next phase is the test migration strategy. This phase is for the source and destination for test migration. And the last phase is the test selection strategy. For this test is send the suitable tests to the appropriate destination. Let's talk about the first strategy of dynamic balance. The first strategy is called the gradient model. In the gradient model, the underload processor will inform other processor of their state or their load condition. Then the overload processor will transform portion of load to the nearest underload processor. In this strategy, there are 2 different important parameter. One is called low watermark and the other one is high watermark. So if a processor load is below the low watermark, is considered as underload processor, and if the load of the processor is higher than the high watermark, then the processor is considered as an overload processor. In the beginning, all processors are set to Wmax. Wmax is the dimension of the system. For example, in the figure 1, Wmax dimension is 4, and the approximative function is showing below the figure 1. As the function say, the Ni is the nearest processor of the processor P. So which means is if the underload processor in the figure 1 is 0, then the nearest one processor is +1. As the distance go further, distance will be add up 1 again and again. So if the distance is 1, then the nearest processor will be set to 1, and the distance is 2, processor proximity will be set to 2. After the proximity is set to each of the underload processor, and then the overload processor will look around, see which processor near the overload processor got the lowest approximated, and then the overload processor will send a unit of load to the underload processor. For example, in the second column, second row, the black circle is indicated as the overload processor. Surround this overload processor, the E0 processor got the lowest approximated, which is E0. That means the overload processor indicate in black color will send a unit of load to the 0 processor. The second strategy is the sender initiated diffusion. The idea of sender initiated diffusion is the overload processor will send load to the underload neighbors. Each neighboring node will calculate a value that is less than the average load in the domain, then inform other near neighbors of their load level. Then they will use the load level value to determine the rate of the load that the overload processor is going to transfer. For example, in the figure 2, if the black color processor in the figure 2 assumed as the overload processor and has 4 near underload processor indicated in gray color, after certain calculation, each near underload processor has a weight to adopt corresponding portion of the load from overload processor. So which means is if the underload processor 1 has a weight is higher than the underload processor 2, then the overload processor will send more load to the underload processor 1 than the underload processor 2. Next will be the receiver initial diffusion. The receiver initial diffusion is similar to the send initial diffusion. It's just the opposite way. The underload processor will request the load from the overload processor. When the underload processor drop down to the preset threshold, and then will be like raise hand say I'm available to help the overload processor, and then the overload processor will be sent half of load to the underload processor. So for example, if the overload processor has total 8 load, and then will be sent 4 of the load to the underload processor. So each time only will be sent half. And next slide will be the hierarchical balance method. For this method, the basic structure is shown in the figure 4. Let's look at the left side of the slide. In the domain 1, there are 3 different processors. Each square is one individual processor, and the top one is the root processor, and the bottom 2 is 2 different leaf processor. In this method, 2 leaf processor will update their current state and the load condition and the location of itself, and then all this information will be uploaded to the root processor, and then the root processor will do some kind of calculation. The root processor will send the migration information to the lower level leaf processor. For example, if in the left leaf processor E0 in the domain 1 is overloaded, then the left leaf processor E0 will be sent a portion of the load to the nearest domain, which is domain 2 left leaf processor 2. In this method, left leaf processor will be only send the load to the left leaf processor. And the next one is the dimension exchange method, which is my favorite. For this one, the step is shown in the figure 5. From the paper, they say they will do the balance each dimension if we lay out the CPU in 3 dimensions, which is X, Y, Z coordinate. Then the balancing will be happen in each coordinate first. Figure 5A is doing the balancing in the Y direction. Figure 5B is doing the balancing in Z direction, and then C will be like the X direction. After all this direction, all the CPU inside the figure 5 will be balanced. When I first time look at this paper, it's really hard to understand how the dimension exchange method works. I draw some picture in the below to show how they work with the specific number. So inside the bottom, the most left picture is the initial condition. We can see there's a circle inside the initial condition. Each circle is indicated as a processor. For the number inside the circle represent the load of the CPU. As we can see, the number inside the CPU is all different, means they have all different initial condition. They are not balanced. And then let's move to the step 1 is the balancing in the y direction. In the y direction, we can see do the balancing in the y direction. 1.5 will be plus the 0.5, and then the total will be 2, and then they will average out for these two processor will become 1. So for the other three pair processor will be do the same thing. So now all the y direction CPU they are balanced out. And then step 2 will be the balancing in the z direction. The previous processor low number will be put to the side of the CPU, and then we will do a final result showing in the center of the circle. As we can see in the step 2, the balancing in the z direction, after they are balanced, all the left side number is become 1.5 and the right side number with 3.5. So in this stage, 4 CPU is balanced, and then other 4 CPU is already balanced. And then we move to the next step is step 3. In the step 3 is after 2 direction balance, this is the final stage balance in the x direction. As we can see, all the number inside the CPU they are matched together is all balanced to the 2.5, which is perfect. In this slide is talk about the implementation. All these 5 different strategy for the dynamic balance is running on the Intel IPS-C Hyperq server. And the first step for the implementation is test and analyze user synthetic data, consisting of the set of the test with the random computation requirement and executed explicit loop, which means is they feed in really large number to these 5 different strategy and try to see these 5 strategy they are working well or not. And then the second step is observe the strategy performance and balance the artificial application. In this step, they are using a real problem to apply to this 5 strategy, which is the branch and the bound job schedule problem. In this slide is the implementation of the result one, which means it is they fit in really huge data, big data to test out these 5 strategies, see they are working well or not. We can see on the top is the table 2. Table 2 is the parameter used for the test method, and all the formula is showing for each strategy. In the figure 6 on the slide right hand side bottom is showing the results of this test. And we can see dimension exchange method and the RID, which is the receiver initiate diffusion, is perform the best. And this slide is the implementation and the result too. For this slide, it's just showing the parameter set up for the real problem, which is the branch and the bound problem, and also is showing the result of branch and bound problem. For the branch and bound problem, which is in the say in the simple way, is for different worker A, B, C, D, they have done job 1, 2, 3, 4, and they spend some of the hour to finish job 1, 2, 3, 4, and they try to find out, for example, if for worker A, when they doing this job, which perform the best. In the figure A, as we can see, this one it got a very similar result as the result 1. The DEM and RID will be outperform all the other strategies. In conclusion, this paper they talk about 5 different strategies for the dynamic balance. The DEM and the RID outperform all the other strategy, but the DEM has a problem if one of the CPU is overloaded. They need to take certain step for the dimension to balance all the CPU out. They will take a little bit time for the information transfer, and the RID is the best result because it only requests some of the overload CPU to send the half of load to the underload CPU. Beyond the paper, I got some further idea for research. In this paper, they talk about the dynamic load balance for the CPU. So what I'm thinking is maybe the dynamic load balance is able to apply to the GPU. Currently, many people doing the AI, neural network, deep learning, they are using the GPU to train the model. If we can apply the dynamic load balance to the GPU, then we'll shorten the time for training the model. In the end, I would like to say thank you to everyone that watched my presentation. I would like to do better in the future to improve my presentation skill. Thank you again.